I want to talk about an interesting problem that struck me while I was watching a video of people playing Dungeons and Dragons. And the problem is to calculate the probabilities of getting a given roll when you have advantage or disadvantage. Um, so advantage in Dungeons and Dragons is where you would roll two 20-sided die and take the greater of the two. Disadvantage would be to roll two and take the lesser of the two. Um, and in the game, it sort of represents when you have a strategic advantage, like when a particular. Well, I guess you really only use a 20-sided die for attacks. So I guess if you're um, say if someone is like trudging around in the mud and you're trying to attack them, right? They would have a harder time dodging you when you try to attack them. So you would have advantage to attack them. And I guess for disadvantage, I guess you could imagine if you're trying to attack someone but they've like thrown sand in your face, so you have a hard time seeing. You'd have a harder time making the attack. So that's when disadvantage would be used. So the problem is to um, calculate the new probability of getting a 1, 2, or etc. For each of the rolls. So I've got a spreadsheet here, and we're going to fill it out. 1 to 20 here. That. Okay. And I think we can all agree that the standard probability for rolling a 1, or really any of these, is going to be 1 out of 20. Okay. So each of these has the probability of rolling, has a probability of 1 in 20. But let's say, for example, if you're rolling with advantage, right? Well, then the problem becomes slightly different. Then you'll. I guess the simplest approach is, well, you're taking the max of two rolls, and I'm going to refer to the die as a d20 because that's what you call a 20-sided die in Dungeons and Dragons. So you roll two d20s and you pick the highest, right? So what are the different ways that you can get a 1 out of that roll, which is 1 would be the highest out of the two. So just like over here, I guess if you represent it like an ordered pair, one way to get a 1 would be to roll double ones, right? But then if you rolled 1, 2, or 2, 1, and really anything else, if you're taking the highest, these would both give you a roll of a 2, right? This is the only way that you can get a roll of 1. Okay. So there's really only one way to do it. And then if you're using, there's a way to calculate a probability. You count the number of ways, the number of successes, the number of ways that you can have a success, and divide by the number of total possibilities. So if you're counting the total different rolls that you can have for rolling two die, well, the first roll has 20 possibilities, second roll has 20 possibilities. You multiply that, you get 400. So therefore, this probability has to be 1 out of 400. Okay. On to the next one. Okay, so how can you roll a 2? Well, like we just had over here a second ago, you can roll a 2 with a 1, 2, or a 2, 1. And you can also roll it with a 2-2. Now, an interesting thing that I had trouble getting over, it is not correct to count 2 twice. Okay? So regardless of the fact that we're counting these as different, right? Just switching their order makes them count as different. But that doesn't work. It doesn't make sense to do that for the 2. You don't count 2 twice. So you wouldn't have 4 possibilities here. You would really only have 3. And the best way that I can explain that, other than just saying that's the correct way to count, is well, if you look at a simpler example, right? Say you're flipping 2 coins, and I think most people have, when they're introduced to probability, this is sort of the thing that everyone remembers. There's 4 possibilities, right? When you flip 2 coins, and those possibilities are heads, heads, tails, heads, heads, tails, tails, tails. Right? So, because of the way we're counting the possibilities, right? We have to it has to work this way. Because as you can see here, to get these are the only 4 possibilities. You don't count heads, heads twice, despite the fact that these 2 are reverses of each other. And then also, I suppose, if it helps, you can think of it as like a like a tree diagram. The first coin is a heads, and then the next coin could either be another head or tails, and then tails, heads, tails, tails. Right? So this isn't the best drawing, but I think you can imagine that, like, here's the first roll, and then these are the possibilities. Well, I guess technically it might make more sense to have it like this. Hey, why'd you stop being centered? Thank you. Okay, heads, tails, heads, tails. Right, so you just combine this. Heads and then heads, heads and then tails, right? That can give you all these possibilities. Right, so as long as we're counting it correctly, everything should work out. So this gives you 3 out of 400. Right, okay. Well, how would we calculate 3? And maybe, I don't know, maybe you can see that there's going to be a pattern here, but let's just try it out just to make sure. How can you roll a 3? Well, you're picking the highest, so as long as there's a 3 in there, it's all good. So 1, 3, 3, 1, 2, 3, 3, 2, and then 3, 3 should be all. These are basically all the ways that you can have at least 1 3. And that gives you 5. Okay. Good. And I should also point out that if we're going to make a general formula for this, we'll know it's correct if at the end of the day it all adds up to 1. So I'll just put a total thing here. Get out. Alright, that adds up to 1. This obviously won't add up to 1 just yet. Okay. Right, so what's the formula here? Well, it's definitely going up by 2 each time, the number of possibilities, right? 1, 3, 5. And if we were to, we have this to work off of, right? So we could do 2 times 1, which is 2 minus 1 to get us 1. So I think that's the formula. I think the formula is simply 2n minus 1. Over 400. And, okay, yep, same results for each. 2 times 2 minus 1. So that's 4 minus 1, so this is 3. That's 3. 2 times 3, which is 6, minus 1, that gives you 5. Okay, and if we're right, we should be able to fill this down, and it sums to 1. Yes. So we know that we found a good formula for advantage. All right. So what about disadvantage? Now, okay, so for disadvantage, here's the thing. It's a little bit weird, because it actually might be easier to start with the ways that you can roll a 20. But let's just think about, okay, how many ways can you roll a 1 when you're doing disadvantage, where you're taking the minimum, right? Well, if there's a 1 in for either of the die, then you'll have it. You'll have a 1 because there's nothing less than a 1, right? Well, geez, how many ways can you get a 1? Because even if you roll 20 and a 1, that still counts as a 1. And then 1, right? So that's not so nice. Maybe if we, 2 times 19 minus 1. Let's put that there for now. 2 times. Okay. And then, let's come down and look at this one, because I have a feeling there are a lot fewer ways that you can roll 20. In fact, there's only one way. If you're taking the minimum, if you roll a 19 and then a 20, you get a 19. So you have to roll 2 20s. So that's just going to be one possibility in 400. Right? But then, okay, so for 19, you can roll a 19 and a 20, because you're taking the least. 20 and a 19, 19, 19. So that's 3 out of 400. And maybe you're seeing now that it's going to be the same pattern, but backwards. So 0.0025, 0.0025. It's not a coincidence that that's the case. But the fact that this is different should probably be a clue that there's something slightly off. I must have miscounted. 2, 3, 4, 19. Oh. Plus 1. I don't know why I put minus 1. I was subconsciously trying to match the form of this with this. But no, yeah, this is 2 times 19 plus 1, yeah. Alright, so, but if you're coming from this direction, right, if you do it this way, you can get a formula here. There's different ways to get this formula. But I think the smartest way is to do, let's see, how can we get 1? Yeah, maybe we can just do 20 minus that, 20 minus n plus 1 over 400. So that's 0 plus 1 over 400. This is going to be 1. 20 minus 19 is 1 times 2. So 20 minus 19 is 1 times 2 is 2, and then plus 1 is 3. Yeah. Okay. So this formula should work. There you go. And, alright, and if you wanted to exactly match the form of 2 times something minus 1, you could probably do 20 minus that plus 1 minus 1. And get the same thing. Alright. So, well, awesome. I guess that's it. But, you know, there's more that you could do, right? What happens if we generalize this idea? What if you're not just rolling 2 die, but say, for example, you're rolling 3 and you pick the max or the minimum, right? So I guess you could call that 2 times advantage. How would you go about calculating these probabilities? Is it going to be just as easy? Probably not. But let's think about it. Okay. You've got 2 times advantage, so you're taking the largest out of 3 rolls, 3 d20s. How many ways are there to roll a 1? Well, if there's anything higher than a 1, it's not going to be a 1 anymore. So literally has to be 3 ones. Okay. And then it's no longer out of 400, but it's out of, well, what's 20 cubed? 8,000. Right? Okay. Cool. So maybe it's going to be simple, right? How many ways can you roll a 2? Well, there has to be at least 1 2 in there, right? So 2, 1, 1. 1, 1, 1, 2, 1. 1, 1, 2. So that's all the ways you can have 1 2. How many ways can you have 2 2s? 2, 2, 1. 2, 1, 2. 1, 2, 2. And then how many ways can you have 3 2s? Well, there's exactly 1 way. Okay. Well, that's not 3 possibilities. That's like 2 times 3 possibilities plus 1. Which is interesting. I wonder if there's a way that you could do it recursively. But regardless, this is not as simple of an answer, right? So finding a formula is going to be a little bit more tricky. So, but let's put this down, 6, 7. Okay, so we got 7 out of 8,000 for that one. Now, how can we roll a 3? Well, there has to be at least 1 3, right? Okay. So same as before. 3, 1, 1. Oh, jeez. Let's get this centered again. Okay. And well, there'd be just as many possibilities over here. Right, so that's 7 plus. Well, now we could also roll a 2, and it would be ignored. So I guess you could do 3, 1, 2. 3, 2, 1, 3, 2, 2. Oh boy. And then you could also do... Well, I guess you could have 1, 2, 2, 1, and 2, 2 in place of each of these pairs of ones, right? So that's 3 times 7. So now it looks like we have 28. What? Oh my goodness. Yeah, okay. So it looks like there's 28 possibilities. And well, oh no, wait. Because this, it's only 6, so 3 times 6. So 7 plus 18. Oh my goodness. Relax. Okay, so it looks like there might be 25 possibilities. And there doesn't seem to be an obvious pattern here. It's kind of messy and not really obvious. Like, you could probably figure something out. 25 over 8,000. Right? But 1, 7, 25. There's not the pattern isn't as clear, and it looks like it's not linear. It's like increasing very quickly. So we've got to think of a different way to count these, right? And I'm not even sure if 25 is right. So let's think of this differently. Okay. We can simplify the problem a little bit. The domain of numbers we're looking at, or the domain of combinations, triples, because we know that the only way to roll a 3 is it has to involve numbers that are no greater than 3. That's definitely true, because since you're picking the largest, it's always going to be numbers no greater than 3. So it's got to involve the possibilities using 1s, 2s, and 3s. Okay. How many of those are there? Well, since there's 3 possibilities for the first one, 1, 2, or 3, 3 for the second one, and 3 for the third one, there's 27 possibilities, right? Great, but then some of those don't work, right? Because we can include 3, 3, 3. That's definitely will give you 3. But you can't include 2, 2, 2. And you can't include oh, I think this is really wrong. Don't worry about that. Ignore that. You can't include 2, 2, 2. You can't include 1, 1, 1. You can't include 1, 1, 2, 2, 1, 1. Right? You can't all those things, you know? Stay centered, gosh dang it. Except for you. You can be uncentered. And if you try to count all of the combinations from this group that don't give you a 3 in the end, where the max isn't 3, well, you're gonna end up counting exactly how many that we counted last time. Right? These are all the possibilities. These are all the triples with numbers no greater than 3 that don't have any 3s. Right? Okay, so it would be 27 minus... It should be 27 minus these, but also minus this. Because this wouldn't have been... The triple one is not included in this, right? So it's 27 minus all the ways that you would roll a 2 or a 1, which is 27 minus 7 minus 1, which is 19. So this was very wrong. So if that's the case, well, that also doesn't really lend itself very well to a formula, because it's kind of it's recursive, right? You have to calculate all the previous ones to be able to calculate the next one. So that's not quite the answer we're looking for. So the real answer, the answer that's going to get you to a nice formula, the best way to do it is to actually go back a step. Let's go back and think about advantage, or single advantage, right? So imagine that all of the possibilities were arranged in a grid, right? This isn't the full grid, but just imagine, right? And I guess this is the... so the first position is, these are all ones for the first position, second position, third position. Okay. You arrange them in a square. And of course it's going to be square because there's going to be 20 ways here, 20 ways there. That'll give you all 400 possibilities. Okay. And there's actually this very interesting pattern that arises. So if you... How many ways can you roll a 1? Well, the only way to do that with single advantage is to roll 2 ones, right? So that's this. And then, well, how many ways can you roll a 2? Well, that's going to be all of this stuff. Right? Because you can roll, as long as there's 1, 2 in there, it'll give you these possibilities. And then how many ways can you roll a 3? Well, it's going to be these outer possibilities right here. Okay. And if you wanted to calculate for any one of these, right? So let's say I wanted to calculate the number of ways that I could roll a 3 without knowing all the previous ones. Well, like before, you take the whole square of possibilities, so that's 3 times 3. There's going to be 9 possibilities. And you subtract off everything in this section, which is actually another square. So you do the 3 by 3 square minus the 2 by 2 square to get the number of possibilities to roll that will give you 3. And the same concept works for rolling a 2, because you take the 2 by 2 square and you subtract 1, giving you 3. So if we come back here, and we were to give a different formula for single advantage, well, you would want to do, for this one, for the very beginning, you could do 1 squared minus 0 squared. This would be 2 squared minus 1 squared. 3 squared minus 2 squared. 4 squared minus 3 squared. So in general, that is this squared minus this minus 1 squared. N squared minus n minus 1 squared. And if we fill that formula down, still works. Same exact results. Okay. And, well, for disadvantage, you can just imagine that you're sort of working this from the top right corner. So how many ways could you roll a 20? Well, this square would have 20, 20 in it. Then how many ways can you roll a 19? Well, this would have 19, 20, 20, 19, and 19, 19. So it's sort of the same process, just starting from a different corner. So if you wanted to do the formula here, it might take a bit of thought. We want to start here. But yeah, so just remember that this should give us 1 in the end. And I think it should use the same logic of 20 minus something, right? So it should be 20 minus plus 1 squared minus 20 minus that squared. So it would be 20 minus 20, 0, plus 1 squared. So 1 squared minus 0 squared. And the same process should trickle up, giving us the exact same numbers. Okay, awesome. And as it turns out, the same argument works when you're in 3 dimensions, when you're working with triples. So you can do a 2 times advantage with, if you're thinking of it like a cube instead of like a square, which would just mean basically the same formula, but everything is to the 3rd power. So literally just change the powers to 3. And that's still 1. And that's still 0.875, and that's still that. That's still 1, and this would be, this should be 5, right? 2 cubed, which is 8. What was it? It was 7. 7, yeah. 2 cubed, which is 8, minus 1, which is 7, yeah, exactly. And then this is going to be, yep. So you continue, you follow this down, and it all adds up to 1. That means we have the right formula. And then, well, let's clear this out for disadvantage. Same exact concept. You literally just take the same formula. You take the same formula, and you change squareds to cubes. And of course you're no longer divided by 400, but instead 8,000. And this should match this, and it does. And we fill it down, and it adds up to 1. So in general, if you wanted to calculate any number of advantage or disadvantage, you use either of these formulas. It's 20 to some power, always, and then you just change the powers here. Okay. So let's see if I can't figure out how to make that happen. So what I've done now is I've made the formula work in general, and I've made it so that it takes the first character from the left of whatever in this box. So for 2 times advantage, we had 3 to the third power, and then this is 20 cubed. So it's basically 2 plus 1 in all of these. That's why you've got left plus 1 in all of these. So that way, if I want to look at 4 times advantage or 5 times advantage, I can just change one number. And you'll see in each case it adds up to 1, as it should. Oh, come on. I don't want to look at all the decimal places. Oh, well. So there we go. We've solved it in general. And what would be nice at this point would be to look at a picture of exactly how it changes as you go from single advantage to double to triple, etc. So I'll put that together right now. So here's the graph, and I plotted. So this is the graph for advantage at least, and I've got the standard right here, where it's a flat probability for each of the rolls, or for each of the rolls, the numbers that you can get, and I plotted up to 4 times advantage, and as you can see here. Wow, that's actually quite a change. Yeah, like immediately the chance of getting a 1 is drastically reduced. And in general, the type of function that each line represents, they're all polynomial, but they all increase in power each time. So in the beginning you've got a constant function, and then you've got a linear function, which is single advantage. And then you've got a presumably quadratic function, 2nd degree, and then this is the 3rd degree, and then this is 4th degree. And then similarly for disadvantage, I've got the graph here. It's the same kind of idea, and naturally for disadvantage, you have a higher chance of rolling low. Yeah. And advantage gives you a higher chance of rolling high. And the relationship is very much not linear. Pretty neat, actually, to look at. Okay, but we're not done there. We have sufficiently generalized this. That is definitely a fact. We've got. You can calculate as many advantage or disadvantage as you please, using the formula something to a power minus that minus 1 to a power. But you can go. You can sort of formalize it, and if you've taken a course in statistics, this notation will kind of make sense. If you haven't, well, it's gonna be nasty, but I'll try to make sense of it. So it's really just stating what we know a little bit more precisely and with different notation. So if you're just doing a standard roll, right? You're just rolling a d20, for example. It's going to be what's called a discrete uniform distribution. So that means that each of the possibilities has the same probability of coming up. And that's just what this symbol represents. This is a uniform distribution on a set, and it's going to be a set of consecutive integers. And of course you put the lowest integer. That's what this is saying, to put the lowest integer here, and then the highest integer here. And then this is just the set. This just means that a and b are integers right here. Okay. And the uniform distribution, the discrete uniform distribution, is already very well understood. Like, you can look up on Wikipedia, it tells you all this stuff. I just wrote it again because we're going to add stuff to it. Okay. Every probability distribution has either a PDF or a PMF. Okay. PDF is probability distribution function. PMF is probability mass function. You use PMF when you're talking about discrete stuff because, well, discrete means there's no in-between values. So like what we're dealing with just integers. We're not dealing with, you can't roll 1.5, for example, right? So, and the probability mass function just tells you what the probability of each of the possibilities are. And in this case, if you have a discrete uniform distribution over a certain number of elements, say that number of elements is n, then the probability is going to be 1 over n because it's evenly distributed. All of them have the same probability and it's shared equally. Just like if you're flipping a coin, each possibility is 1 over 2 and there's 2 possibilities. So that's what 1 over n comes from. And if you didn't want to use the letter n, you could say you could do b minus a plus 1, and that will also tell you how many elements you have. And if you want to know the mean or the expected value of when you take a sample from the distribution, which means basically when you roll a die, it's going to be the sum of the two endpoints divided by 2. So the average roll on a d20 is not 10, it's 11 over 2, or 10.5. And that doesn't mean that 10 or 11 are more likely. It just means that, well, if you rolled it a bazillion times, added them all up, divided by how many rolls you made, it would tend to 10.5. And then CDF, that's the cumulative distribution function. CDF, when you're talking cumulative, it has to be continuous. I'm not sure why, but it just is. And cumulative means that let's say we came over here. Let's use our 4 times disadvantage as an example, right? And if you were doing the cumulative distribution function, you would be keeping a running total, right? So you basically ask the question, what's the probability of getting something less than or equal to this value? So in the beginning, of course, it would just be this. And then it would be this plus this. So I believe let's see if I can make a formula out of that. Actually. Right, so if you're talking about the cumulative distribution function, the CDF is the probability of less than or equal to. So it would be, what's the probability of rolling less than or equal to a 2? Well, it's this number. Fairly high because you have 4 times disadvantage. And all of these are just running totals, right? And at the end, of course, you're going to have 1. What's the probability of rolling less than or equal to a 20 on a d20? 100% probability, because there's no other possibilities. And so this floor function right here is just so that that basically gives you a step function, and it puts it sort of just connects the dots for you. It makes the discrete continuous, this floor function here. So anything less than 1, so between 0 and 1, you would get the floor of that is always going to be 0 until you get to anything less than 1 will be 0, and then when you get to 1, it's going to be equal to 1. That's what the floor function does. And right, so it turns out that this is the CDF. And this makes sense because let's think of the D20 example, right? The probability of rolling less than or equal to 5, right? So let's kind of follow this formula. A is the smallest number, right? So it would be 5 minus 1 plus 1. So that's 5. And then over how many possibilities there are. So it's basically counting the number of numbers less than the number that you're currently at. And then, of course, dividing by how many total numbers there are. That'll give you the CDF of the uniform discrete. But now, what we did is, well, we took a bunch of uniform discrete distributions, and for any number of them, we took the min or we took the max. So this is saying let's use x with a subscript number to represent each of the samples that we're taking from the uniform distribution, right? Basically, how many die we're dealing with, and from 1 to x is how many we have, right? And x is the total number of die we're dealing with. So if you want to look at, let's take the max of each of those die rolls, right? So this is advantage. X minus 1 would tell you the level of advantage. So you take the max out of all those samples, and then this is the new information that you get out of it. So this is basically what we calculated. You do the current number you're on minus the least number plus 1. So let's plug in, let's say we're doing advantage, right? Which is what this is. And you plug in 1, okay? So you plug in 1 as your k. A is the lowest number, so 1 minus 1 plus 1. So 1 to the x minus, and then this would give you 0 to the x. Divided by, and then for our D20 example, there's 20 possibilities, so 20 to the x. And that's basically what this formula represents. Now, as for taking the average, I couldn't work out a general formula. So this right here is just basically the definition of mean when you have a probability distribution. and I guess I can demonstrate that. Say, for example, you wanted to find the average of a probability distribution, which is where you have a probability distribution is where you have the value and then its probability, right? What you do is you do the value times its probability a bunch, and then you sum all those up. Oops. So as I mentioned before, for just the for the simple case, you can use this formula, which is the first time plus the second, or first plus the last over 2, right? And that's why you get 10.5, because the formula is correct. You do 20 plus 1 over 2. Same thing, right? But when you're dealing with advantage or disadvantage, I couldn't find a clever formula like the first plus the last over 2. Not one that works for every case, and I'm pretty sure there isn't one. I'd be interested to know if someone could figure out one that like looked nice, because I'm sure you could like shove this into. So f of k is this. So you add up k times this in for all of the values you have. I'm sure you could get something that looked very nasty, but I was hoping for something nicer, and so that's why I just left it like this, because this is just the definition of mean. And then what's interesting here is that there is actually a nice CDF. It turns out that you can actually just take the regular CDF and raise it to the power of the number of samples that you're taking. Yeah, and so that's not specific to that's not a characteristic that's unique to the uniform discrete distribution. It actually works regardless of what distribution you're working with. And I figured out that nice little that nice little tidbit. I looked that up, and this is pretty nice. So then, if you're working with the minimum, these are the formulas for that. Just like our actual formulas. Let's see if the comparison is pretty good. Disadvantage. So you take the highest number minus the current, don't do that, plus 1. Highest number minus the current plus 1. Right? And then same thing for the mean. There's no nice formula. And then for the minimum over a number of distributions, the CDF looks like this. And again, it's no accident. This works for any distribution. So this is about as generalized as you can make the process that we went through. This is the deepest dive. Well, I'm sure you could go deeper, but this is about as general as I was willing to go. So that's about it. I hope you enjoyed. Thank you very much for watching, and I'll see you next time.